Yo, what's up? Yo, what's up? I'm still talking a lot about fiction writing, quantum anything, and Bevan machines, stuff like that. So let's get started with quantum physics and quantum dynamics by using a quantum electronic circuit with a quantum electronic circuit, a Hadamard gate. We're just going to start with a Hadamard gate, not a whole quantum computer, not, the basics of quantum physics. You know superposition, you know entanglement, you know those kind of things without explanation. In the name of Jesus, the Hadamard gate is a fundamental building block in quantum computing. If we are looking at it from a quantum electronics or circuit architecture perspective, its primary job is to act as a superposition generator. So it generates superpositions. It takes a definitive classical-like state and puts it into a balanced quantum coin flip. So it's not just going to flip a coin, but it's going to hold it's going to enforce or generate a superposition. The mathematical transformation, when you pass a standard computational basis state through a Hadamard gate, it maps the state to an exact equal superposition of 0 and 1. So on input 0 turns into the plus state, state 0 plus state 1 over square root of 2. Now the square root of 2 is there because those are vectors, not just numbers, so they have magnitude and direction. Input 1, state 1 turns into the minus state. State 0 minus state 1 over square root of 2. I do not know why 0 would be plus and 1 would be minus, but let's just flow with it. In matrix form, the Hadamard operator is represented as 1 over square root of 2 times the matrix 1, 1, 1, negative 1. When this matrix acts on the state vectors, the 1 over square root of 2 factor ensures that the total probability amplitudes scale correctly, preserving the normalization of the qubit state vector, keeping it securely on the surface of the block sphere. I don't know block sphere, man, but I do know that there's a lot of excess geometry involved in this computation, which I am thinking has a lot to do with the reason why these things worked. So I want a circuit that inputs state 0 or 1, applies Hadamard gate, and outputs appropriately. All appropriately. That'd be a basic circuit. So to build a quantum circuit, it takes an input state 0 or 1, applies a Hadamard gate, and extracts the output. We need to handle two main phases: superposition and measurement. Okay, yeah, okay. You put it in superposition, you measure it, collapse it. Here's how the circuit is structured conceptually, mathematically, and in standard code. So there's a quantum circuit notation. The system is read from left to right. It requires one quantum wire, qubit, and one classical wire to hold the measurement result. Now, what does that have to do with a quantum computer? We'll make a gigantic leap real quick. What does that have to do with quantum computer. The CPU chip is full of quantum gates. It has a clock to push the quantum wave forward. So that gives us the time domain wave equation. QRAM, I'll just use my analogy here, QRAM based on pinball. There's going to be an registers for accessing memory addresses, as well as operator codes built into the chip. The architectural concept you are mapping out with integrated registers, opcodes, a central clock, and a structured wave progression mechanism is a fascinating way to conceptualize a unified physical processing engine. It sounds a lot like designing a deterministic time-step emulator or a physicalized pinball routing matrix for states. However, looking at how actual quantum computing hardware is being engineered today, so I am now thinking about old hat. The way these components function is fundamentally different from a classical CPU. Here's how those concepts translate into the real architecture of a quantum computer. The CPU chip versus the QPU. Classical CPU chip contains billions of static etched transistors that switch on and off to form classical logic gates. A QPU does not have a physical pile of hardware quantum gates welded inside it. Instead, the chip contains an array of physical qubits, such as superconducting transmons or trapped ions resting in a blank state. How gates happen. The quantum gates, like Hadamard gate we discussed, are not physical objects. They are spatio-temporal control pulses, microwave fields, or laser sweeps sent down control lines from an external chassis to hit the qubits. Then we'll talk about the clock real quick. In a classical CPU, the clock is a crystal oscillator generating a square wave that acts as a gatekeeper, forcing electrons to settle into deterministic 0-1 voltage rails before the next cycle begins. In a quantum processor, there is no system clock pushing a wave forward step by step to a bus. Instead, the entire system evolves continuously according to the time-dependent Schrodinger equation, where H hat is the Hamiltonian. So what are we? So what is this hybrid? A quantum signal generator? Exactly. So we have a quantum signal generator that we can generate quantum computational signals and send it into, I don't know, what do we send that into? Exactly, you hit the nail on the head. At the macro scale, the actual engine driving a quantum computer is a highly synchronized, ultra-precise classical signal processing matrix. Control stack, classical to quantum. The system functions as because like it said, it's deterministically quantum. So we program in the quantum signal we want to send, and it sends it. Uh, what we can do is do classical code sent to an FPGA to an AWG to the QPU chip. Okay, so let's control a QPU with this deterministic generator through assembly language. Control engineering at this level bridges the gap between discrete classical logic and continuous analog physics. To control a QPU with a deterministic signal generator, you need a specialized low-level assembly dialect that maps directly to timed waveform execution. In real-world quantum hardware control, this is achieved using frameworks like OpenPulse or hardware-specific assembly language like EQASM, executable quantum assembly. So the structure of quantum pulse assembly, unlike classical assembly, which relies heavily on jumping based on condition flags, quantum pulse assembly relies heavily on time execution and port channel targeting. The language needs to control channels, which physical coaxial line drive receives the signal, waveforms, the exact mathematical envelope shape, timing, exact clock cycles or nanosecond timestamp to ensure phase coherence. So we can set core instruction set architecture as a set frequencies, set phase, play, delay, and capture. And what we now have is a Hadamard gate and assembly code through our generator. Because a Hadamard gate is physically a combination of rotations, often implemented as a pi/2 rotation around the y-axis, followed by a pi rotation around the x-axis, or vice versa, depending on the frame mapping. The assembly, so that's going back, I think, the way you want to convert state 0 to plus and state 1 to minus. The assembly language maps it to a precise time pulse plays back. So it says define a channel, drive channel 0, DAC port 1, with qubit 0 on the control line. Define channel, read channel 0, DAC port 2, qubit 0 readout drive. Define channel, ACQ channel 0, ADC port 1, qubit 0 signal capture. So 3 channels, 1 for drive, 1 for read, 1 for ACQ, whatever that means. Define waveform envelopes in the generator's memory. Define waveform pi2 pulse, Gaussian, would be a Gaussian waveform with sigma 10 nanoseconds, duration 40 nanoseconds. Define waveform read pulse with a square wave, duration 2000 nanoseconds. Why? I'm going to tell you something, I have no idea what I'm talking about right now. Main execution block, start sequence. This is your main right here. Reset phase, drive channel 0. So you're resetting that drive channel 0. And you want to pulse in Hadamard. In a virtual Z-frame architecture, H is often applied as a Y90 pulse, followed by a frame rotation. So you set the phase to 1.578 on drive channel 0. You play that drive channel 0 with the pi/2 pulse at 0.45 amplitude. Shift the phase to 3.1415 on drive channel 0. Deterministically, you align that with a 20 clock cycle delay and then you basically play it and capture it and end it. This is basically a signal generator control unit assembly code on the generator. It processes it through a strict execution pipeline inside an FPGA or custom ASIC. Okay. So we can have the generator emulate different quantum CPUs. Right? Yeah, you absolutely can. In fact, that is exactly how the absolute bleeding edge of quantum control engineering works. And I guess we look at what the signal looks at. So we could have a superconducting QPU, trap diode QPU, neutral atom QPU. Dual photon well QPU. Because I'm thinking about making these little miniature electronic quantum like onboard stuff. So the state 0 is localized in the left well, state 1 is localized in the right well. What we do is design a crystal components with photon source that acts as electronic components, dual quantum well. Integrating a photon source directly into an engineered crystal component to create a solid state dual quantum well structure is a powerful hardware paradigm. In physics and semiconductor engineering, this is often realized using coupled quantum dots or site-controlled semiconductor heterostructures. We don't need to know too much, like black box this at 5 volts to milliamps, just for the hell of it. Black boxing this monolithic optoelectronic crystal component at 5 volts, 2 milliamps shifts our perspective from microscopic quantum physics to macro-scale electrical engineering. So now we have a pinout for a source, a drain, and a control pin. So, hook this up to a one of those waveform plotters, and let's send our signal. We got to be real careful with signals through it as input quantum waves evolving via a clock pulse. So it's not just Schrodinger. It's Schrodinger-Bevan. It's Schrodinger-Bevan. It's Schrodinger-Bevan. So we have Schrodinger-Bevan wave equation based on discrete time. Booyah! Has anybody ever thought about that? To formalize this setup, we need to replace the continuous time derivative in the standard Schrodinger equation with a discrete time-stepping operator that matches your deterministic system clock. And I don't know math. I don't know enough to do this. Okay, cool. Now I have no idea what's going on. So let's program an input for the component from the wave generator. A sweep. We'll sweep through it. To program our frequency or amplitude sweep into our deterministic signal generator, we need to generate a series of time-step assembly instructions that dynamically alter the control Hamiltonian at every tick of the master system clock. And we're going to chirp it, or an amplitude sweep, adiabatic passage. We've got an assembly routine for the quantum sweep signal that we're not going to really read it, and we're going to get a resulting waveform plot for the quantum component. Channel 1 is the system clock. It looks crazy to me. I don't know if that's the way that's supposed to look. The V control, channel 3, the quantum. I'm gonna tell you, I have no idea. So can a circuit with this component built into a war headgear see humans and animals in pitch black darkness and perfectly EQ the environment instantly and adaptively? Let's find a use for this thing. From a semiconductor and sensor engineering standpoint, you have actually described a highly specialized real-world technology that would operate a bit differently than a sci-fi scanning visor, which are describing using engineered quantum wells inside a crystal lattice to detect living targets in total darkness. Maps closely to an existing class of military and aerospace technology known as quantum well infrared photodetector array. So we have a thermal photon hits the chip, instant current spike, high-speed ADC FPGA algorithm evaluates, adjusts the bias pulse for a dynamic EQ shift. Okay. There would be a realistic engineering trade-off with cryogenic requirement. So you need a Cryocase, for build. Yes, exactly. If you are building this into a practical piece of hardware, A Cryocase or cryogenic vacuum housing is the absolute non-negotiable foundation of the entire mechanical build. Without it, you'll have thermal noise problems. You have smearing the waves, so vacuum jacket, so on and so forth. That was kind of fun. So instead of building an entire quantum CPU, we built a quantum electronic circuit for a particular purpose of seeing in the dark and hearing through any kind of noise. But you're going to have a cryogenic case built into your heads-up display. Anyway, peace out.